Okay, so this is an implementation of Autoencoder using TensorFlow 2.10. And same way you can import dataset, and we have a Python script that allows us to import different datasets from UCI data repository. One of the things we do, and you need to make sure that you are doing the same thing in your code, that you have to scale the data. In this particular case, I'm using the min-max normalization. So what it does is it's converting all the feature values between 0 to 1.
Okay.
Okay, are you doing this?
Yeah, yes.
Okay, so once you do that, here what we are collecting, and don't forget to document or comment each and every line if possible, so that other readers can understand. So here is my input data, and this is the number of samples, this is the number of dimensions we have. And here we are using a special type of initializer, which is called a Glorot uniform distribution. So we are sampling the first initial values of the weights from this Glorot uniform distribution. That's the first sampling thing we're doing, okay? And then what we're doing is we are converting the NumPy array to tensor data, TensorFlow tensor, the same way you did in PyTorch, okay? And then what I did is, in your case, you have your recon and you have your image, right? Those two pieces, right? Here we are passing same X data to training inputs and the same X data to the training outputs. Okay, because they are learning the same thing. And here what I did is I put together the equation, mathematical equations that define the autoencoder. So in this case, I'm saying autoencoder consists of two parts, the encoder part and the decoder part. Encoder part from input encoder data to low dimensional embedding, right? That's the encoding part. In your case, you're making it from 20-dimensional to 4-dimensional, right? Do you follow that? So what is the mathematical equation for that? The mathematical equation would be the 4-dimensional hidden response at the hidden layer, right? Would be the ReLU activation function. This is the weight times input plus bias, right? And then what we are saying that we're going to add another hidden layer. So currently in your autoencoder, you just have one hidden layer, right? So if you want to extend it for multiple hidden layers, you can do that easily. So if that is the case, then I'm saying that H02 is the next hidden layer. And the way we get to the H02 is then our input will be the output of the previous hidden layer times a new weight, because this time we're going to get a new weight and your new bias.
The new bias.
Okay, so here what I'm taking is the dimension of H2, that means the dimension of the second hidden layer is half of the dimension of the first hidden layer. Okay, so this is my encoder part. This is my encoder part. In the decoder part, we return in from the opposite direction. So in the decoder part, what we do here is we get this output, right? This is our final this is our, so in a decoder, what do? You're in a decoder, your input will be this guy, right? Input will be this guy, and you have to use this W02, and in this case, W02 will be the transpose of the other matrix, right? And then you get the Y01 for the second hidden layer, because your encoder part will have two hidden layers, your decoder part will have the same two hidden layers, right? And you get Y01, and from Y01, you get the Y estimate. So this is the reconstructed thing, right? So our cost function would be in such a way that we will try to minimize the error between this guy and what? And the input.
And the actual one.
At the actual input. But in the middle, we have two hidden layers in the encoder part, two hidden layers in the decoder part, okay? So this is once again the autoencoder class, and this is how I'm implementing this thing from scratch, right? So this is the W01, W02, which is for the encoding unit. B01, B02 is for the two hidden layers of the encoding unit, right?
Okay.
And then we have B01 and B02 for the decoding unit. Now you have to understand, these weights will be just transposed. And if you transpose this weight, you will get these weights for the decoder unit. So you do not have to, in this, you see, autoencoder definition, you do not have to have separate weight variables.
Right.
Because the same weight variables will be shared for both decoder and autoencoder, decoder and encoder. However, your biases will be different. Okay, I'm putting the biases as different. And then NACT is your activation function for the encoding unit. DACT means the activation function for the decoding unit. It may be the case that you may end up using different activation functions for different unit. And this is the call function. So what happens is once you create an autoencoder model, you can execute this autoencoder model by triggering this call function. So what this call function does is basically creates the architecture of the autoencoder. So what I did here is very simple. You have this equation and this equation. I just implemented these two equations here. You see this?
Yes, yes, yes.
H01 and H02. Now, why did I keep these two separate? Because when I'm considering ReLU, I'm using the ReLU activation. When I'm considering sigmoid, I'm using the sigmoid activation. Other than that, the equations are the same.
Right.
Okay. And then how do I get the weights for the decoding unit? Simply transpose the weights of the encoding unit. Very simple.
Right.
Right. And how do I then what is the next part? Next part is to implement the equations for the decoder part. So here are my two equations. What are the two equations? This equation and this equation, right? So what I'm doing here is I'm putting these two equations where? Here. Keeping it separate. If I intend to use ReLU, then it's going to implement ReLU with sigmoid. And finally, I get this my Y estimate. So this call function, this model will return what? The Y estimate.
The Y estimate.
Right? Okay. So, and then I have a function that calculates the loss. And in this loss function, I can define my own custom loss. What I have here is when I put model, that means I'll be sending an autoencoder model object, right? This is a class. So I have to create a model object. Once I will be sending this model object and you call this model object, it will trigger this call function, call method. Okay. So what's happening here is in the model, you have to pass the input, right? You have to pass the input because as you can see, when you're passing X, that's the input, right? So you pass the input and what will be the output of this model? This Y estimate.
It's the Y estimate.
And we know our target. What is our target? Target is basically the same input.
The actual one.
Right.
Yes.
So that is giving us the error. And then what we have to do is this error will be a vector because let's say you have 64 samples in a batch. It will calculate the error for each of those samples. So what you want to do is you have to take the mean squared error across all the samples. So what you do is if you pass this error into this TF squared, that's going to take the square of the error because some of those error would be negative, some of those error could be positive. You take the square of the error and then you reduce it to one single mean value. So this will be just one scalar single value mean squared error across all the 64 samples in your batch of data.
Okay.
Is that clear? So that's the loss function. Once again, we have Atom, we're using Atom Optimizer, and this is the first time we're calling this autoencoder constructor function. And as you can see, when I'm putting these things here, the constructor takes all these parameters, right? This is the constructor, right? So I'm creating an autoencoder model object by initializing these guys, right? That's why we call it init. Why do we call it init? Because it initializes an autoencoder object with these initial parameters. Okay. So once we have this one, we have this model, we are defining how many epochs you are going to run it. Okay. And we are also setting the parameters. So here you can see that I have direct explicit access to the weight values. You see this? So what are my parameters? 2 weight matrices, right? 2
And 4
bias
biases.
matrices, bias vectors for the encoding part, 2 bias vectors for the decoding part. Because
Decoding.
these are the parameters I need to learn, I need to train, okay?
Mhm.
Then you have this train function. And inside the train function, you use this gradient tape. Remember, I gave you this assignment, gradient tape. So in a gradient tape, what you do here is first you calculate the loss. So by how do you calculate this loss? Loss is basically this loss function. It takes the model input, and target. So once you put this one, it's going to create the loss value. What is this loss value? This is actually the mean squared loss across all the training sample. That is what will be coming out here. So once we have the loss value, based on the loss and the given parameters, we can calculate the gradients. So what these grads will produce is it's going to produce the gradient, basically the derivative of this loss, rate of change of this loss with respect to the rate of change of these parameters.
Okay.
That's the gradients it will be calculating, right? And then what I have to do is I have to tell my Mr. Optimizer, which is Atom Optimizer in this case, hey, Atom Optimizer, just apply those gradients. What I mean by apply those gradients is if W was some old initial value, now you get a new value of W by taking the old value plus the gradient, the grads of, let's say, parameter. Let's say, what are the parameters? I have this parameter, the gradient of 0, 1. So the gradient of 0, 1, W is 0, 1 will be stored here. I will take that gradient of 0, 1, apply it to the old gradient, right? So this is the gradient I calculated, right? This is the gradient I calculated, and this is the parameter. That means, because this grad is a list of all the gradients. That means the size of these grads will be same size as this one. How many elements you have here? 6.
6.
Right? So, and these are the 6 parameters. So these grads will contain all the updates for these 6 individual parameters. So once I apply this gradient, it's going to do something like this. W new, so it's going to be WH01 new, right? It's going to update the W10 based on its WH0 on old, and whatever grads it gets from this gradient computation, and update that iteratively. So that's my train method. Now I come into the for loop, right? So in the for loop, what I have to do is I'm running it for, let's say, 1,000 epochs. I have this train, right? And in the train, I have to pass what? The model object, input, and target. That's it. Rest of the things will be taken care of. And you know my training inputs and my training outputs, and you just print, right? And as you can see, it's kind of learning, right? It's kind of going down from some epoch, right? So one of the things you have to make sure that if your learning rate is too small, if your learning is too small, your update will be very slow. That means you will need more number of epochs to converge. If your learning is too high, your update will be very fast, but that may not reach the global minimum.
Yes.
You know those things, right?
Yeah.
You just run it and you get it. So the important thing about this code is you have full access to all the weights and parameters, biases, and everything else as you need to. Okay. So do you think that this code will be useful?